Hello, today we're talking about Taylor and Maclaurin series. Finally, this is the last section in this chapter. I want to apologize ahead of time. My puppy Philip is chewing on a bone near my feet, so if you hear that in the background, I'm sorry. So we're going to do a theorem, a definition, and one example today. So the theorem we're starting with is the form of a convergent power series. It says if f is represented by a power series, f of x equals the sum of a sub n times x minus c to the n for all x in an open interval I containing c, then my coefficient a sub n is equal to the nth derivative of f at c divided by n factorial, and then we can write out our series of the form f of x equals f of c plus f prime of c times x minus c plus the second derivative of f at c divided by 2 factorial times x minus c squared, and so on and so forth, and it's an infinite series. So this is very similar to the Taylor and Maclaurin polynomials, except now we're doing infinite version. So let's go ahead and prove this. So the first thing we need is we need to consider a function, or consider a series. So consider the power series. That is the sum from n equals 0 to infinity of a sub n times x minus c to the n, which we're going to say converges with an interval of convergence R. All right, so if that's true, then we get that f of x equals a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared plus a sub 3 times x minus c cubed, and so on and so forth. If I take the first derivative of that, my constant a sub 0 goes away, and now my first term is going to be just the constant a sub 1, and then I'm going to have 2 times a sub 2 times x minus c plus 3 times a sub 3 times x minus c squared, and so on and so forth. And then if I take this second derivative, yes, I have a low battery. Second derivative, now the a sub 1 goes away, and I get 2 a sub 2 plus, I'm going to bring down that exponent of 2, and I get 2 times 3 a sub 3 x minus c. And then my next one would be a 3 times 4 oops, wrong color. 3 times 4, and then I would have an x minus c squared, and the pattern would continue. Let's do a couple more derivatives here, see if we see the pattern. So then if I take the next derivative, the third derivative, I'm going to change this. Instead of 2 times 3, I'm going to write that as 3 factorial times a sub 3. And then my next one, I bring down the 2. And so then I get 2 times 3 times 4, which is the same thing as, well, 2 times 3 times 4, x minus c. And then when I take the fourth derivative, we see that this I can rewrite as 4 factorial a sub 4 plus dot dot dot. Okay, so in the end, when we take the nth derivative of this function, we're going to get n factorial times a sub n is going to be our first term, plus n plus 1 factorial times a sub n plus 1 times x minus c, and so on and so forth. Now if we evaluate this at x equals c, we're going to see that f of c is just going to be 0 factorial times a sub 0. Remember, 0 factorial is 1, so that's just a sub 0. F prime of c is going to equal 1 factorial times a sub 1. So that's just a sub 1. The second derivative at c is going to be 2 factorial times a sub 2. The third derivative at c is going to be 3 factorial times a sub 2, no, a sub 3, and so on and so forth. So in general, we found that if you want to solve for the a sub n, I can divide by, so here, like this right here, divide both sides by 2 factorial. I found that the second coefficient is f double prime of c divided by 2 factorial, and the third coefficient is the third derivative of f at c divided by 3 factorial. So in general, we can say that f of n of c equals n factorial times a sub n, or a sub n equals f, the nth derivative of f at c divided by n factorial, which was what we were supposed to prove, so QED. Okay, now we have the definition of a Taylor and Maclaurin series. So if a function f has derivative of all orders at x equals c, then the series, which is the sum from n equals 0 to infinity of the nth derivative of f at c divided by n factorial times x minus c to the n, is called the Taylor series at c. And once again, we have the special case where if c equals 0, then we're going to call it a Maclaurin series. So this is identical to Taylor and Maclaurin polynomials, except now we're doing infinite instead of ending at a specific spot. So we have our first example, and our first example says use the function f of x equals sine x to form the Maclaurin series and determine the interval of convergence. Okay, so let's start like we always do, where we go ahead and take some derivatives. So if I start with my function is sine of x, and then go ahead and take first derivative is cosine x. Second derivative is negative sine. I'm going to scroll up here so I have some more room. Third derivative, negative cosine. Fourth derivative is sine. And our good old friend, the fifth derivative, is cosine. Probably didn't have to do 5, but I'm just going to make sure. And now I evaluate each of those at 0. So sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. And cosine of 0 once again is 1. So we can see the pattern there. So we have a pattern. Yay, we like patterns. And then when we continue this, we can see that our series from n equals 0 to infinity of f of n 0, the nth derivative at 0 divided by n factorial times x sub n, right? Because our c value is 0. I'm just going to write it out, is f of 0 plus, oops, that should be a plus sign, not an equal sign, plus the first derivative at 0 times x, plus the second derivative at 0 divided by 2 factorial times x squared, and then plus the third derivative at 0 divided by 3 factorial times x cubed, and the pattern continues. So we are going to get, when I fill in the pieces, 0 plus 1 times x plus 0 divided by 2 factorial times x squared plus negative 1 divided by 3 factorial times x cubed plus 0 divided by 4 factorial times x to the 4th plus 1 divided by 5 factorial times x to the 5th. And if I continued the pattern, I would get 0 divided by 6 factorial divided by x to the 6th, and then negative 1 divided by 7 factorial times x to the 7th. And we see that all of the even powers go away. So I'm just going to end up with x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial minus x to the 7th divided by 7 factorial plus ... the pattern continues. And so if I wanted to write this in series notation, summation notation, I'm going to have, we like to start at 0, so n equals 0 to infinity. And we know it's alternating, so I'm going to put my negative 1 in front. And the first term is positive, so at n equals 0, I want a positive 1, so I just put n as my exponent there. And I want all of the odd exponents of x. So if I have 2n, that means it's even, and I want the odd ones. So 2n plus 1 will get all of the odds. And I also want to divide by that same exponent being factorialized. I don't know if that's a word, but we'll pretend it is. And then we have to figure out that where this converges, right? So let's do the ratio test. So by the ratio test, I want to take the limit as n goes to infinity of negative 1 to the, negative 1 to the n plus 1 times x to the 2 n plus 1 divided by 2 to the n plus 1 factorial times 2n plus 1 factorial divided by negative 1 to the n and x to the 2n plus 1. And I want that to be less than 1. And so here we go. Limit as n goes to infinity. And the negative ones don't really matter because I am taking the absolute value. So on the numerator, I have 2n plus 1 factorial. And then on the denominator, I have 2n plus 3 factorial. And then over here, I get an x to the 2n plus 3 divided by x to the 2n plus 1. I want that to be less than 1. And so I end up with, and I'm looking as n goes to infinity. Well, the denominator is always going to be bigger because factorials, this factorial is larger than the factorial on the numerator. So let's see here. I get a, let's write it out though. Limit as n goes to infinity. I have a, well, the whole numerator is going to cancel there, and I get a 2n plus 3 times 2n plus 2. Everything else will cancel. And then I have a x squared at the top. And I want that to be less than 1. Well, as n goes to infinity, that will always be less than 1 for all x. So this converges for all x. All right, so here's my answer. My answer is this for all x values. All right, that's the video today, so go ahead and try the homework.